IPv6 was developed by the Internet Engineering Task Force, IETF, I'm sure you looked it up, to deal with the long-anticipated problem of IPv4 address exhaustion. So IPv6 is intended to replace IPv4. IPv6 became a draft standard in December 1998 and became an Internet standard on the 14th of July, 2017. So instead of 32-bit addressing of IPv4, which provides approximately 4.3 billion addresses, IPv6 uses a 128-bit address. So that theoretically gives us 2 to the power of 128, or approximately 3.4 times 10 to the 38th addresses. Big number. You can check my math later, but stick with me for now. I mean, the actual number is slightly smaller, as multiple ranges are reserved for special use, or they're just completely excluded from use. But with a rough calculation, the total number of possible IPv6 addresses is more than 7.9 times 10 to the power of 28 times as many as IPv4. The two protocols, IPv4 and IPv6, are not designed to be interoperable, complicating the transition to IPv6. However, several IPv6 transition mechanisms have been devised to permit communication between IPv4 and IPv6 hosts. In addition to offering more addresses, IPv6 also implements features not present in IPv4. Simplified header. IPv6's header has been simplified by moving all unnecessary information and options, which are present in the IPv4 header, to the end of the IPv6 header. The IPv6 header is only twice as big as an IPv4 header because that IPv6 address is 4 times longer. End-to-end connectivity. Every system now has a unique IP address and can traverse through the Internet without using NAT or other translating components. After IPv6 is fully implemented, every host can directly reach other hosts on the Internet with some limitations involved, like a firewall, organization policies, and stuff like that. Auto-configuration. IPv6 supports both stateful and stateless auto-configuration mode of its host devices. This way, the absence of a DHCP server does not put a halt on inter-segment communication. Faster forwarding and routing. A simplified header puts all unnecessary information at the end of the header, like we saw earlier. The information contained in the first part of the header is adequate for a router to make its routing decisions, thus making them as quickly as looking at the mandatory header. IPsec. Initially, it was decided that IPv6 must have IPsec, making it more secure than IPv4. This feature has now been made optional. IPsec, Internet Protocol Security, is a framework of open standards for helping to ensure private, secure communications over Internet Protocol networks, IP networks, through the use of cryptographic security services. IPsec is an end-to-end security scheme operating in the network layer. While some other Internet security systems in widespread use, TLS and SSH, operate in the upper layers, IPsec can automatically secure applications at the IP layer. No broadcast. Though Ethernet and Token Ring are considered a broadcast network because they support broadcasting, IPv6 does not have broadcast support anymore. It uses multicast to communicate with multiple hosts. Mobility. IPv6 was designed keeping mobility in mind. This feature enables hosts, such as a mobile phone, to roam around in different geographical areas and remain connected with the same IP address. The mobility feature of IPv6 takes advantage of auto IP configuration and extension headers. Extensibility. One of the major advantages of the IPv6 header is that it is extensible, adding more information in the option part. IPv4 provides only 40 bytes for options, whereas options in IPv6 can be as much as the size of the IPv6 packet itself. What is the IPv6 packet, you ask? You came to the right place. An IPv6 packet is the smallest message entity exchanged via the Internet Protocol across an IPv6 network. But stay with me here. The packets consist of control information for addressing and routing, and a payload consisting of user data. The control information in IPv6 packets is subdivided into a mandatory fixed header and optional extension headers. The fixed header starts an IPv6 packet and has a size of 40 octets, which means 320 bits. Its format is shown in the slide. Version is constant 6. Payload length is the size of the payload in bytes, including any extension headers. Hop limit replaces the time to live field in the IPv4. Well, I think source address and destination address fields are fairly obvious. Extension headers carry optional Internet layer information and are placed between the fixed header and the upper layer protocol header. 128-bit IPv6 addresses are written using hexadecimal, as opposed to dotted decimal back in IPv4. Because a hexadecimal number uses 4 bits, this means that an IPv6 address consists of 32 hexadecimal numbers. These numbers are grouped in 4s, giving 8 groups or blocks. The groups are written with a colon as a separator. An IPv6 address example is shown in the slide. So because of the length of the IPv6 addresses, various shortening techniques are employed. The main technique being to omit repetitive zeros, as shown in the example. So as I mentioned before, in IPv4, an address is split into 2 components, right? A network ID and a host ID. This was done initially using address classes and then later using subnet masking. In the unicast addressing of IPv6, it's done in the same way. The first step is to split the address into 2 parts. The address is split into 2 64-bit segments. The top 64 bits is a network ID, and the lower 64 bits is the host ID. The most significant 64 bits are used for routing, and the least significant 64 bits identify the address of the interface or host. This block is derived from the actual physical or MAC address in practice. So if we look at the most significant 64 bits in more detail, we can see that it's split into 2 blocks of 48 and 16 bits. Now, the least significant 16 bits are used for subnets on internal networks and are controlled by a network administrator. The most significant 48 bits are used for the global network addresses and are used for routing over the Internet.